So let's talk about some new examples, and these are going to be trig functions and e to the x. So why do we need to sort of take a pit stop and do some examples with trig functions and e to the x? Well, many of you aren't going to be studying mathematics just for pure mathematics' sake. If some of you are, great, it's a really cool thing to do. But a lot of the reason why people need to study mathematics is to apply it to problems in the real world. And if you try to apply mathematics to real world problems, and you want to take derivatives and solve problems, etc., trigonometric functions and exponential functions are going to come up very naturally. So we need to talk about them. So let me just say, first of all, what the derivatives of these of some basic functions are, then we'll do a whole bunch of examples with them. And this will at least allow us to do some extra examples that don't just have to be polynomials. So, of course, we have our most basic trig functions are sine x and cos x. And of course, what are these guys? Let me just quickly, I'm not going to go into this in too much detail, but if you have sort of a triangle in the xy plane, so let's say this is x, this is y, let's say this is a line of length 1, if you have this angle here and this right triangle is theta, well, what we're going to have is we're going to have that the sine of theta is going to be the ratio of this side over this side, and the cosine of theta is going to be the ratio of this side over this side. So one way to put that, and indeed I'm writing this because this is going to be very useful for a lot of problems, is the base length of this triangle here is going to have to be cosine of theta, and the height of this triangle here is going to be sine of theta. And it's very useful to have this picture that you can just sort of draw out because you're going to be using it again and again in various calculus-related things. But this is how sine and cosine works. So this is sort of the standard formula. Another way to put this is that sine is y over r and the cosine is x over r, if you will. There are other functions. Let's just note that the tangent is going to be y over x. So we have that the tangent of theta is going to be indeed sine of theta all over cosine of theta. But this is just, hopefully you've seen trigonometric functions before. There's certainly a lot to say about them, how to graph them out, how they behave. They have many properties, but this is just a very quick refresher, or perhaps a quick definition. If you've never seen these before, I would take a moment and at least, go to the textbook you're working from now, go to Wikipedia, go to Desmos, whatever you'd like, and sort of take a look at these functions. But what we can do is we can differentiate them. So if you have to work through these functions because they've come up in some problem, we at least can say that the derivative of sine x is going to be cosine of x, and that the derivative of cosine of x is going to be minus sine x. So this is pretty straightforward, pretty easy to work through. And I won't belabor this, but in fact, how you compute these derivatives is with some known special limits as well as some fun trig identities. So let me just sort of let you know about how to compute the derivative of sine at 0. Well, what is the derivative there by definition? Well, that's of course the limit as h goes to 0 of sine of 0 plus h minus sine of 0 all over h. But it's a very quick thing to see that the sine of 0 is 0. So this is the limit as h goes to 0 of sine of h over h. But if you watched the previous video series, this is one of the limits we talked about in some detail there. This is one of our special limits that ends up being equal to 1. And guess what? It turns out that 1 is cosine of 0. So that's how we can at least see that this fact is true for x is equal to 0, and sort of taking this argument, adding some trig identities and running with it, tells you things in general. Notably, one of the reasons why I like talking about these fun special limits is because they're neat on their own, they're fun to work with and useful to work with on their own, but they also have other applications, notably to derivatives. Now, another function that you're probably going to see, or you probably have seen and are going to work with, is e to the x. And let's just draw a rough graph of this function. But again, if you want a nice graph of a function, Desmos, Wikipedia, your textbook, etc., etc., there are many, many resources in this digital age to see pictures of functions. But nonetheless, this function looks roughly like this, and it models what we refer to as exponential growth. And this function has a very special property. We have that the derivative, and I'm going to introduce this notation here because sometimes a function is written in such a way that it's not nice to write a prime next to it. So sometimes if you want to say the derivative of a function, you write d by dx. This is just notation of a function. So the derivative of this function is actually itself, which is sort of cute. It's not a lot of functions, really only multiples of e to the x satisfy this property that they're their own derivative, but indeed that's how it works. So, with my tiny little bit of preamble about what these functions are, what we're going to sink our teeth into is that now these functions, which are either familiar to you or will become familiar to you very soon, we know how to differentiate them. Let's do some examples differentiating these functions, or functions involving these functions, and also using the product rule, the quotient rule, and the chain rule. Okay, so let's do some examples with this. So we'll start off easy and we'll use each one of the major rules that we've learned already. So first of all, as an example, let's talk about f at x is equal to x times e to the x. So this is not that complicated of a function, but one thing that I will let you know is if you sit down and try to go through the definition of the derivative for this function, you're going to have a real hard time. It's going to be a very complicated limit if you can even get all the way there. And you're going to have to basically redo the calculation of what the derivative of e to the x is in the first place if you use the limit definition here. Suffice it to say you don't want to. But given what we've learned, and given that we know the derivative of x and the derivative of e to the x, this is actually a very easy problem for us to solve, because we can solve this with, of course, the product rule. So what's the derivative of this guy? Well, it's the derivative of x times e to the x. The derivative of x is 1, so it's e to the x, plus x times the derivative of e to the x, but the derivative of e to the x is itself, so it's just e to the x plus x times e to the x, or if you prefer, e to the x times x plus 1. A fair bit easier than doing this calculation any other way, and sort of maybe just, and please do try to do this computation just for 5 minutes. Write it down on the back of a piece of paper. See how complicated it is, just to give yourself a little bit of confidence about why we really like to just sort of know lists of basic derivatives, know the basic rules of differentiation, and understand how powerful this is and how much computational power this gives us. So that's that example there. We're done. We've finished it entirely. Let's talk about maybe another example with, let's say, the chain rule. Another pretty simple function. Let's say we have gx is equal to e to the x squared. I say it's a simple function. It's a simple function because we know the rules of differentiation that we've learned so far. Not an easy function to work with just given the definition. But what do we do here? Well, this is a chain rule problem. We're going to let our u be equal to x squared, if you like that notation. So I guess I've already called something f up here, but I've drawn a little line. We're going to let u be equal to x squared, and our f at u is going to be equal to e to the u. So we can use the chain rule now to differentiate this guy, and we get that g prime of x is just going to be, well, the derivative of f when you plug in x squared, but again, the derivative of this guy is itself. So this is just e to the x squared. Then we have to multiply this by the derivative of, and of course, let me just write this, I'm using the chain rule here. And then we're multiplying this by the derivative of x squared, which, as we've now computed a whole bunch of times in a bunch of different ways, is 2x. So maybe it's a little nicer to write this as 2x e to the x squared, but nonetheless, we're done. We couldn't handle this example without the chain rule, but with the chain rule, it's a very easy example. All right, so going forward, and there are these examples, the sky's the limit with how difficult they can get, but just note, you have these rules, you can use them with the sort of table of information I gave you. We can now add sine x, cosine x, and e to the x to our menagerie, and you can enjoy them, working with them in various examples. But wait a second, we're missing something, aren't we? Because in our examples, one thing that I talked about is I talked about tan x, and I said it was this, and I didn't give you a formula for what the derivative of tangent was. Well, how can I do that? I told you that I'm going to tell you how to differentiate the trig functions, but I didn't give you the derivatives of one of the trig functions. Why didn't I do that? Well, the tangent is a quotient of two functions we know how to differentiate, so we can compute the derivative of the tangent function with the quotient rule. So what is this? Well, it's the derivative of the top guy times the bottom guy. The derivative of the top guy is cosine of x, so we get cosine of x times cosine of x, and then minus, and then the top guy times the derivative of the bottom guy. The top guy is sine of x, the bottom guy is minus sine x, because the derivative of cosine is minus sine x. And then downstairs we get cosine of x all squared. Now, what is the top? Well, when we take cosine of x squared, we often write this as cos squared of x, and similarly with sine squared. This is just notation, but it's something that comes up a lot. You'll certainly see it in your textbooks and other resources, so I'll include it. So what we have upstairs is cos squared of x plus sine squared of x all over cos squared of x downstairs. But you've probably seen the Pythagorean identity before, so yes, unfortunately, trig identities come up and they are going to be important for our calculations. We have that sine squared x plus cos squared x is always going to be equal to 1. This is essentially the Pythagorean theorem, notably to the picture on the previous board, if you want to go back there in the video. Apply the Pythagorean theorem to that picture, and you get why this guy has to be equal to 1. So this is equal to 1 over cos squared x, and let me give you a quick definition. Sometimes people write secant of x, which you might have seen before, as 1 over cos of x. So sometimes we refer to 1 over cos squared x as secant squared of x, because we of course also, instead of writing secant of x squared, notationally one often writes secant squared of x. So yeah, that's how to differentiate tangent, and if you know the other trig functions, like for example, if you wanted to differentiate secant, or cosecant, or cotangent, the other ones which you can quickly look up what they are, they all get differentiated fairly easily, again, by the quotient rule. So that's why I really only had to include sine and cosine in my list.